Hello everyone. In previous lectures, we have studied the definition of unilateral Z-transform and the unilateral Z-transform for some typical signals. In this lecture, we will study the properties of unilateral Z-transform. The contents include these properties. First, we will study the linearity property. The property is described in this expression. It's similar with the Fourier transform and Laplace transform. This is a time shift property. For the causal sequence, the property is described in this expression. For the non-causal sequence, the time shift property is described in this expression. Here's some explanation. This is a non-causal sequence. If we delay 1 unit for this non-causal signal, we can get this signal. This part is this signal. This value delayed to this position. The signal includes these two parts. For the unilateral Z-transform, we can get this result. Similarly, if we delay this signal in 2 units, we can get this signal. This part corresponding to this signal. And these two values delayed to these positions. To the unilateral Z-transform, we can get this result. For example, for this signal, we determine the unilateral Z-transform. We have now this signal. Its unilateral Z-transform is this fraction. According to time shift property, we can get this signal's Z-transform. According to linearity properties, we can get the Z-transform for this signal. Because this signal is a finite length sequence, so the ROC is this expression. Here is another example. Determine the unilateral Z-transform for this signal. The signal can be represented as this equation. According to the time shift property, we can get the unilateral Z-transform for this signal. This is a geometric series of infinite lengths in the ratio, so its ROC is in this expression. Here we can find this number 1 is the pool of the fraction. For the convolution property, it can be expressed in this expression. It means convolution in time domain, multiplication in Z domain. The ROC is the common part of these two ROCs. For example, we calculate the unilateral Z-transform for this signal. By the convolution property, we can get its unilateral Z-transform in this equation. We have now this signal's Z-transform and this signal's Z-transform. According to the property, we can get the signal's Z-transform. Here is the ROC. This is a common part of the ROC and this ROC. Here is another example. Determine the unilateral Z transform for this signal. We'll find this signal can be represented as the convolution of this signal and this signal. So, by the convolution property, we can get the unilateral Z transform for this signal y of k. Here is another property, the summation property. Xk is a causal signal. The property is described in this expression. Here is the verification for this property. This is a convolution of these two signals. You can get this equation because x of k is a causal signal, so it starts from 0. So we can get this result according to this equation. This one corresponding to this one. This Rx corresponding to this X. The region of convergence is the common part of this region and this region. Here is another property, exponential weighting property. It's also termed Z-domain scaling property. This property is described in this expression. For example, for this signal to find the unilateral Z transform, we have known the unilateral Z transform for this signal. So, according to the exponential weighting property, we can get the unilateral Z transform for this signal. Here is another property termed Z-domain differentiation property. It's also called linear weighting property. This property is described in this expression. It means multiplication by k in a time domain corresponding to differentiation with respect to z and the multiplication of the result by minus z in the z domain. For example, determine the unilateral Z transform for this signal. We have known the unilateral Z transform for this exponential signal. According to the Z-domain differentiation property, we can get the unilateral Z transform for this signal. It's the ROC for this Z transform. Here is the initial and the final value theorems. For the initial value theorem, it's described in this equation. For the final value theorem, it's described in this equation. Of course, the ROC of this function should include the unit circle in Z plane. For example, determine the initial and the final value for this signal. According to initial value theorem, we can get the initial value for this signal. If the magnitude of alpha is less than 1, the ROC of this function includes the unit circle in Z plane. So we can get the final value for this signal, xk, is 0. If the causal sequence x and k can be represented as this equation, and the Z transform of finite length signal x1k is x1z, then we can derive the Z transform of x and k as in this expression. Here, the ROC is greater than 1. In this lecture, we have discussed the properties of unilateral Z transform. That's all for today. Thank you.